So cation exchange capacity is probably one of the big things that soil scientists talk about and is really important for a lot of the things that we've been discussing right now. So cation exchange capacity is the ability of the soil to hold and exchange cations. So cations, remember, are positive. I always think of it because I love cats, and so cats are positive. That's how I remember it. So cations. So ions are atoms with electrical charges. So just so you know, like cations are calcium, and magnesium, which is called divalent cations. And we talked about ion exchange when we talked about radium, and we talked about those things before. And that's where you're exchanging for your sodium and your potassium. And then anions are things like sulfate, phosphate, nitrate. So this one's nitrate. NO3 is nitrate. Chloride are negative, so those are anions. So almost all soils at normal at pH 7, around circumneutral pHs, most soils are negatively charged. And so the soils are mostly negatively charged, so they attract the positively charged things. So I showed you that picture of the clay before, and that clay, those plates on there, especially on the edges, are have places for these cations to absorb onto. And when we looked at the organic material before, let me see over here. So we look at organic material on these edges too are great places for cations to stick onto because generally soils are negatively charged. So when we look at it, we've got these negatively charged, they like to hold on to these cations onto there. So cation exchange capacity is due to, well, the organic material content. So like I said, that complex organic material has places to hold on to it. So as you can imagine, we have these beautiful mollisols here. So we would have it. The clay content, so how much clay is in there, because a lot of those plates that are in there, each type of clay has it, but a lot of times clays are very negatively charged. Also, you get that high surface area to volume ratio. So if you guys remember what that is, surface area to volume ratio is that, and this is why clays have a lot of porosity. They don't have a lot of permeability because they actually have a lot of those places in between all those plates for inside of there. So the clay content of the soil makes a difference. And then the types of clays. So if you're talking about a montmorillonite, you have a high cation exchange capacity. But if you have a kaolinite, you'll have a low. If you have an illite, your middle. We have a lot of illates in this area, montmorillonites. We have a lot of these types of clays in this area. So kaolinite, we don't have as much about here. So we have a really, if you think about our soils, we have a lot of cation exchange capacity here. So those soils hold on to all those positively charged ions. This right here, this is just a map showing the average value of microequivalence. So this is how the ability of the soils to go on here. So the darker the purples is more cation exchange capacity. So you get over into Iowa, glorious. And then we get into Illinois. We've got some areas, around the suburbs that are really high. We're still really in the high range. I mean, we're in this pink areas in here. So we've got really high cation exchange capacities and stuff like that in these areas and stuff. And then we go out west, you start to get less of it. And so again, we're really good when it comes to cation exchange capacity. So most soils are negatively charged, and so they hold those cations into there. And then cations are held on exchange sites. So these are the sites that are along the edges of the clays on there. And once they're held onto there, but they're only held on there by covalent bonds. And so they're just held on there, and so they're easy for the plants to take up. So what it is it's easy for the plants to take them up into the root systems. So they get held onto there, and then the plants can come and take in that nutrients that it needs. Anions are not held on soils and are subject to leaching. Okay, so a lot of times these things, if they're anions, they're going to leach out of the soil. So we talked about the zone of accumulation, we talked about the zone of leaching. And then when we look at the types of ions, except for phosphorus, these things will not get held as fast by soil. So when we talked about nitrates and eutrophication and all of these things, this really influences, this moves through the soil faster because it doesn't have any negative places. There's no positive charges onto there. And so we have to be very careful when we put nitrates and these things on soils because they'll just leach right on through because of the cation exchange capacity. Phosphorus is an exception to this because of the way the phosphate bonds work. It'll actually get absorbed onto the soil into there. And so this is what's going on here. You have these soil colloids. So there's these platey. That's what generally soils look like, this plate. And they have all these negative changes. So we get these positive cations coming in, and we get negative ions coming off. And so it releases these nitrates. And so we're having this constant movement of cations and exchanges between them and absorption and desorption of all these ions on there. And so another way of looking at cation exchange capacity is that if we have a cation exchange capacity of 5 versus a cation exchange capacity of 25. So here, if we have a heavy clay, we'd get up to 50. If we get down to sand, we'd get down to a 2. And so common range for these, so all of these will stick onto here. We'll get less clay, fewer positions to hold on to these cations into here. So as we lower on the numbers, less places for these to stay in. So if something's moving in, something is coming off on here. And then more clay, more places to hold on to these ions, more negative charges. We can absorb more of these things and do more exchange with inside of there. So understanding this and understanding how climate impacts it, weather, agricultural practices, really is important for cation exchange capacity. So what are some of the practical applications of knowing about it? So if our soils are between 11 and 50, which we've got around here, we've got a higher clay content. It requires more lime to get the correct requires more lime to correct a given pH. So in there, we have a greater capacity to hold on to these nutrients and a higher capacity for water. Well, if we have these lower ones, we have lower clay. We don't require as much lime, but we're going to leach out everything, and we have really hard to hold on to water. So the really practical part of this is that we've got a soil where we have to add lime, and so you'll see that around here. You'll see the lime. But we've got much better holding, more nutrients available, better for the plants. So this is another reason why our soils are so wonderful around here. The last thing I just want to talk about with soils is, like I said, there is more life below the ground surface, more especially with microorganisms. Microorganisms is just amazing. That's my bachelor's degree. My bachelor's degree is microbiology and chemistry, and then my master's degree was soils. And then finally I got into geology and hydro for my PhD. So, I love science. Just science. So microorganisms are just fascinating. I mean, just think about, like, everything about them is amazing. So what they'll do is they'll colonize onto here. So they'll live in little clumps, and they'll be all over our soil particles. And in fact, less than 1% of all soil surfaces will support the growth of microorganisms. So they live in all these little clumps. And a lot of times if there's plates of clay, I've seen this, where they'll be on certain parts where there's micronutrients that they need, areas they can be in. So they'll clump together in parts, and there'll be other areas where there won't be any microorganisms. So their goal is to maintain their species. So within a gram of soil, there'll be 700 different species of bacteria, archaea, bacteria, all the different names, the actinomyces, all that kind of stuff. And so there's 10 to the 16 bacteria per acre. When you go 3 inches deep, that's how many bacteria are there. And so they're stuck there. So, and what they do is they absorb onto the surfaces, they stick onto the surfaces, and as water and nutrients are going into that vital, when we talked about that wilting capacity, we talked about that water that's on those things, this is where they're at. And so a lot of different things will happen with that. I'm going to pause this. So microorganisms are important. Sorry about the phone call that came in. That's for you guys who know, it was Dr. Gallagher. So in there. And so one of the things that I just wanted last thoughts on this was that, if you look at a soil core, it's so much more complicated than what you think it is. It's got all these macro pores into there. There is different colors usually associated with these things. There's all these holes and roots and all this beautifulness, which, allows for water to transport, nutrients to transport, microorganisms to live on all these surfaces and everything. And when we look at preferential flow paths, which is where is the preferred flow, we talked about the A horizon, the B horizon, and the C horizon, and we look at where these things go down, and they follow root systems in there. So 68% of leachable atrazine, so we talked about atrazine as a pesticide commonly used in this area, remember we talked about that, was lost to preferential flow during the first storm. So what would happen is that it would just land on the top here, and these very complicated things would just go right into the groundwater system. Even if we have clays and everything like that, we get these preferential flows that are in there. And what is the implication for soil fertility? Well, when we think about when we put that nutrients on the top here, what happens to a lot of it? It just goes straight down. Just so you guys know, this is a side note. One of the research projects I'm working on with my grad student is looking at microplastics or nanoplastics, and when they break down in the environment, how do they move through these preferential flow paths? Do these plastics can get into our drinking water supplies? Do they move faster? Because if you put water here and it goes down through this area here, it's going to move faster than maybe water that's going and diffusing into these areas. Do microplastics maybe clog these? Maybe there's clogging that occurs in those things. So we're saying microplastics. So if we have a lot of microplastic pollution or nanoplastic pollution, we're going to clog some of these preferential flow paths. Will it change the soil properties? So this is one of my research projects I'm working on. I know, it's exciting. I'm really fascinated with plastics right now, but that's a whole nother lecture in class and everything else. So that's all we got to talk about soils. There is so much more you can learn about soils. Soils are just amazing. You can take whole classes in it. You can get whole degrees in it. And for my little lectures on it, hopefully I gave you some information about it and got you kind of like thinking about the lands that are around us. And so you're getting kind of like a view of what we have in this area. So, okay.